The Solar System is the gravitationally bound system comprising the Sun and the planetary system that orbits it, either directly or indirectly. Of those objects that orbit the Sun directly, the largest 8 are the planets, with the remainder being significantly smaller objects, such as dwarf planets and small solar system bodies. Of the objects that orbit the Sun indirectly, the moons, 2 are larger than the smallest planet, Mercury. The Solar System formed 4.6 billion years ago from the gravitational collapse of a giant interstellar molecular cloud. The vast majority of the system's mass is in the Sun, with most of the remaining mass contained in Jupiter. The 4 smaller inner planets, Mercury, Venus, Earth and Mars, are terrestrial planets, being primarily composed of rock and metal. The 4 outer planets are giant planets, being substantially more massive than the terrestrials. The 2 largest, Jupiter and Saturn, are gas giants, being composed mainly of hydrogen and helium. The 2 outermost planets, Uranus and Neptune, are ice giants, being composed mostly of substances with relatively high melting points compared with hydrogen and helium, called ices, such as water, ammonia and methane. All planets have almost circular orbits that lie within a nearly flat disk called the ecliptic. The Solar System also contains smaller objects. The Asteroid Belt, which lies between the orbits of Mars and Jupiter, mostly contains objects composed, like the terrestrial planets, of rock and metal. Beyond Neptune's orbit lie the Kuiper Belt and scattered disk, which are populations of trans-Neptunian objects composed mostly of ices, and beyond them a newly discovered population of xenoids. Within these populations are several dozen to possibly tens of thousands of objects large enough to have been rounded by their own gravity. Such objects are categorized as dwarf planets. Identified dwarf planets include the asteroid series and the trans-Neptunian objects Pluto and Eris. In addition to these 2 regions, various other small body populations, including comets, centaurs and interplanetary dust, freely travel between regions. 6 of the planets, at least 3 of the dwarf planets, and many of the smaller bodies are orbited by natural satellites, usually termed moons, after the Moon. Each of the outer planets is encircled by planetary rings of dust and other small objects. The solar wind, a stream of charged particles flowing outwards from the Sun, creates a bubble-like region in the interstellar medium known as the heliosphere. The heliopause is the point at which pressure from the solar wind is equal to the opposing pressure of interstellar wind. It extends out to the edge of the scattered disk. The Oort cloud, which is believed to be the source for a long-period comets, may also exist at a distance roughly 1,000 times further than the heliosphere. The Solar System is located in the Orion Arm, 26,000 light-years from the center of the Milky Way. Discovery and exploration. For many thousands of years, humanity, with a few exceptions, did not recognize or understand the concept of the Solar System. Most people up to the late Middle Ages Renaissance believed Earth to be stationary at the center of the universe and categorically different from the divine or ethereal objects that moved through the sky. Although the Greek philosopher Aristarchus of Samos had speculated on a heliocentric reordering of the cosmos, Nicolaus Copernicus was the first to develop a mathematically predictive heliocentric system. In the 17th century, Galileo Galilei, Johannes Kepler, and Isaac Newton developed an understanding of physics that led to the gradual acceptance of the idea that Earth moves around the Sun, and that the planets are governed by the same physical laws that governed Earth. The invention of the telescope led to the discovery of further planets and moons. Improvements in the telescope and the use of unmanned spacecraft have enabled the investigation of geological phenomena, such as mountains, craters, seasonal meteorological phenomena, such as clouds, dust storms and ice caps on the other planets, structure and composition, The principal component of the Solar System is the Sun, a G2 main sequence star that contains 99.86% of the system's known mass and dominates it gravitationally. The Sun's four largest orbiting bodies, the giant planets, account for 99% of the remaining mass, with Jupiter and Saturn together comprising more than 90%. The remaining objects of the Solar System together comprise less than 0.002% of the Solar System's total mass. Most large objects in orbit around the Sun lie near the plane of Earth's orbit, known as the ecliptic. The planets are very close to the ecliptic, whereas comets and Kuiper belt objects are frequently at significantly greater angles to it. All the planets and most other objects orbit the Sun in the same direction that the Sun is rotating. There are exceptions, such as Halley's Comet. The overall structure of the charted regions of the Solar System consists of the Sun, four relatively small inner planets surrounded by a belt of mostly rocky asteroids, and four giant planets surrounded by the Kuiper belt of mostly icy objects. Astronomers sometimes informally divide this structure into separate regions. The inner Solar System includes the four terrestrial planets and the asteroid belt. The outer Solar System is beyond the asteroids, including the four giant planets. Since the discovery of the Kuiper belt, the outermost parts of the Solar System are considered a distinct region consisting of the objects beyond Neptune. Most of the planets in the Solar System possess secondary systems of their own, being orbited by planetary objects called natural satellites, or moons, and, in the case of the four giant planets, by planetary rings, thin bands of tiny particles that orbit them in unison. Most of the largest natural satellites are in synchronous rotation, with one face permanently turned toward their parent. Kepler's laws of planetary motion describe the orbits of objects about the Sun. Following Kepler's laws, each object travels along an ellipse with the Sun at one focus. Objects closer to the Sun travel more quickly because they are more affected by the Sun's gravity. On an elliptical orbit, a body's distance from the Sun varies over the course of its year. A body's closest approach to the Sun is called its perihelion, whereas its most distant point from the Sun is called its aphelion. The orbits of the planets are nearly circular, but many comets, asteroids, and Kuiper belt objects follow highly elliptical orbits. The positions of the bodies in the Solar System can be predicted using numerical models. Although the Sun dominates the system by mass, it accounts for only about 2% of the angular momentum. The planets, dominated by Jupiter, account for most of the rest of the angular momentum due to the combination of their mass, orbit, and distance from the Sun, with a possibly significant contribution from comets. The Sun, which comprises nearly all the matter in the Solar System, is composed of roughly 98% hydrogen and helium. Jupiter and Saturn, which comprise nearly all the remaining matter, possess atmospheres composed of roughly 99% of these elements. A composition gradient exists in the Solar System, created by heat and light pressure from the Sun. Those objects closer to the Sun, which are more affected by heat and light pressure, are composed of elements with high melting points. Objects farther from the Sun are composed largely of materials with lower melting points. The boundary in the Solar System beyond which those volatile substances could condense is known as the frost line, and it lies at roughly 5 astronomical units from the Sun. The objects of the inner Solar System are composed mostly of rock, the collective name for compounds with high melting points, such as silicates, iron or nickel, that remained solid under almost all conditions in the protoplanetary nebula. Jupiter and Saturn are composed mainly of gases, the astronomical term for materials with extremely low melting points and high vapor pressure, such as hydrogen, helium, and neon, which were always in the gaseous phase in the nebula. Ices, like water, methane, ammonia, hydrogen sulfide and carbon dioxide, have melting points up to a few hundred kelvins. They can be found as ices, liquids, or gases in various places in the solar system, whereas in the nebula they were either in the solid or gaseous phase. Icy substances comprise the majority of the satellites of the giant planets, as well as most of Uranus and Neptune and the numerous small objects that lie beyond Neptune's orbit. Together, gases and ices are referred to as volatiles. Distances and scales. The distance from Earth to the Sun is 1 astronomical unit, or O. For comparison, the radius of the Sun is 0.0047 astronomical units. Thus, the Sun occupies 0.00001% of the volume of a sphere with a radius the size of Earth's orbit, whereas Earth's volume is roughly 1/millionth that of the Sun. Jupiter, the largest planet, is 5.2 astronomical units from the Sun and has a radius of 71,000 kilometers, whereas the most distant planet, Neptune, is 30 astronomical units from the Sun. With a few exceptions, the farther a planet or belt is from the Sun, the larger the distance between its orbit and the orbit of the next nearer object to the Sun. For example, Venus is approximately 0.33 astronomical units farther out from the Sun than Mercury, whereas Saturn is 4.3 astronomical units out from Jupiter, and Neptune lies 10.5 astronomical units out from Uranus. Attempts have been made to determine a relationship between these orbital distances, but no such theory has been accepted. The images at the beginning of this section show the orbits of the various constituents of the solar system on different scales. Some solar system models attempt to convey the relative scales involved in the solar system on human terms. Some are small in scale, whereas others extend across cities or regional areas. The largest such scale model, the Sweden Solar System, uses the 110-meter Ericsson globe in Stockholm as its substitute sun, and, following this scale, Jupiter is a 7.5-metre sphere at Arlanda International Airport, 40 kilometers away, whereas the farthest current object, Sedna, is a 10 cm sphere in Luleå, 912 kilometers away. If the Sun-Neptune distance is scaled to 100 meters, then the Sun would be about 3 centimeters in diameter. The giant planets would be all smaller than about 3 millimeters, and Earth's diameter along with that of the other terrestrial planets would be smaller than a flea at this scale. Distances of selected bodies of the solar system from the Sun. The left and right edges of each bar correspond to the perihelion and aphelion of the body, respectively. Long bars denote high orbital eccentricity. The radius of the Sun is 0.7 million km, and the radius of Jupiter is 0.07 million km, both too small to resolve on this image. Formation and evolution. The solar system formed 4.568 billion years ago from the gravitational collapse of a region within a large molecular cloud. This initial cloud was likely several light-years across and probably birthed several stars. As is typical of molecular clouds, this one consisted mostly of hydrogen, with some helium, and small amounts of heavier elements fused by previous generations of stars. As the region that would become the solar system, known as the pre-solar nebula, collapsed, conservation of angular momentum caused it to rotate faster. The center, where most of the mass collected, became increasingly hotter than the surrounding disk. As the contracting nebula rotated faster, it began to flatten into a protoplanetary disk with a diameter of roughly 200 astronomical units and a hot, dense protostar at the center. The planets formed by accretion from this disk, in which dust and gas gravitationally attracted each other, coalescing to form ever larger bodies. Hundreds of protoplanets may have existed in the early solar system, but they either merged or were destroyed, leaving the planets, dwarf planets, and leftover minor bodies. Due to their higher boiling points, only metals and silicates could exist in solid form in the warm inner solar system close to the Sun, and these would eventually form the rocky planets of Mercury, Venus, Earth, and Mars. Because metallic elements only comprised a very small fraction of the solar nebula, the terrestrial planets could not grow very large. The giant planets formed further out beyond the frost line, the point between the orbits of Mars and Jupiter where material is cool enough for volatile icy compounds to remain solid. The ices that formed these planets were more plentiful than the metals and silicates that formed the terrestrial inner planets, allowing them to grow massive enough to capture large atmospheres of hydrogen and helium, the lightest and most abundant elements. Leftover debris that never became planets congregated in regions such as the Asteroid Belt, Kuiper Belt, and Oort cloud. The NICE model is an explanation for the creation of these regions and how the outer planets could have formed in different positions and migrated to their current orbits through various gravitational interactions. Within 50 million years, the pressure and density of hydrogen in the center of the protostar became great enough for it to begin thermonuclear fusion. The temperature, reaction rate, pressure, and density increased until hydrostatic equilibrium was achieved. The thermal pressure equaled the force of gravity. At this point, the Sun became a main sequence star. The main sequence phase, from beginning to end, will last about 10 billion years for the Sun compared to around 2 billion years for all other phases of the Sun's pre-remnant life combined. Solar wind from the Sun created the heliosphere and swept away the remaining gas and dust from the protoplanetary disk into interstellar space, ending the planetary formation process. The Sun is growing brighter. Early in its main sequence life, its brightness was 70% that of what it is today. The solar system will remain roughly as we know it today until the hydrogen in the core of the Sun has been entirely converted to helium, which will occur roughly 5 billion years from now. This will mark the end of the Sun's main sequence life. At this time, the core of the Sun will collapse, and the energy output will be much greater than at present. The outer layers of the Sun will expand to roughly 260 times its current diameter, and the Sun will become a red giant. Because of its vastly increased surface area, the surface of the Sun will be considerably cooler than it is on the main sequence. The expanding Sun is expected to vaporize Mercury and Venus and render Earth uninhabitable as the habitable zone moves out to the orbit of Mars. Eventually, the core will be hot enough for helium fusion. The Sun will burn helium for a fraction of the time it burned hydrogen in the core. The Sun is not massive enough to commence the fusion of heavier elements, and nuclear reactions in the core will dwindle. Its outer layers will move away into space, leaving a white dwarf, an extraordinarily dense object, half the original mass of the Sun but only the size of Earth. The ejected outer layers will form what is known as a planetary nebula, returning some of the material that formed the Sun, but now enriched with heavier elements like carbon, to the interstellar medium. Sun. The Sun is the solar system's star and by far its most massive component. Its large mass produces temperatures and densities in its core high enough to sustain nuclear fusion of hydrogen into helium, making it a main sequence star. This releases an enormous amount of energy, mostly radiated into space as electromagnetic radiation peaking in visible light. The Sun is a G2-type main sequence star. Hotter main sequence stars are more luminous. The Sun's temperature is intermediate between that of the hottest stars and that of the coolest stars. Stars brighter and hotter than the Sun are rare, whereas substantially dimmer and cooler stars, known as red dwarfs, make up 85% of the stars in the Milky Way. The Sun is a population I star. It has a higher abundance of elements heavier than hydrogen and helium than the older population II stars. Elements heavier than hydrogen and helium were formed in the cores of ancient and exploding stars. So the first generation of stars had to die before the universe could be enriched with these atoms. The oldest stars contain few metals, whereas stars born later have more. This high metallicity is thought to have been crucial to the Sun's development of a planetary system because the planets form from the accretion of metals. Interplanetary Medium. The vast majority of the solar system consists of a near vacuum known as the interplanetary medium. Along with light, the Sun radiates a continuous stream of charged particles known as the solar wind. This stream of particles spreads outwards at roughly 1.5 million kilometers per hour, creating a tenuous atmosphere that permeates the interplanetary medium out to at least 100 astronomical units. Activity on the Sun's surface, such as solar flares and coronal mass ejections, disturb the heliosphere, creating space weather and causing geomagnetic storms. The largest structure within the heliosphere is the heliospheric current sheet, a spiral form created by the actions of the Sun's rotating magnetic field on the interplanetary medium. Earth's magnetic field stops its atmosphere from being stripped away by the solar wind. Venus and Mars do not have magnetic fields, and as a result the solar wind is causing their atmospheres to gradually bleed away into space. Coronal mass ejections and similar events blow a magnetic field and huge quantities of material from the surface of the Sun. The interaction of this magnetic field and material with Earth's magnetic field funnels charged particles into Earth's upper atmosphere, where its interactions create aurora seen near the magnetic poles. The heliosphere and planetary magnetic fields partially shield the solar system from high-energy interstellar particles called cosmic rays. The density of cosmic rays in the interstellar medium and the strength of the Sun's magnetic field change on very long timescales, so the level of cosmic ray penetration in the solar system varies, though by how much is unknown. The interplanetary medium is home to at least two disk-like regions of cosmic dust. The first, the Zodiacal dust cloud, lies in the inner solar system and causes the zodiacal light. It was likely formed by collisions within the asteroid belt brought on by gravitational interactions with the planets. The second dust cloud extends from about 10 astronomical units to about 40 astronomical units, and was probably created by similar collisions within the Kuiper belt.